This video is going to discuss the use of Zener diodes. So in previous videos, we've shown what a normal diode is, and we've also explained the behavior in the forward bias mode and the reverse bias mode using the depletion region formation. So if I just show you the characteristic curve we've studied and we've investigated for a normal diode, and then based on that we can study how this diode is different to a normal diode and in what circumstances we use it. So I'm going now just to show you the characteristic curve we've come across before for a normal diode. Yep, so we've seen the characteristic curve before, where in the forward bias mode means your anode is more positive than your cathode, and when the diode conducts in the forward bias mode, we have this type of characteristic curve where when you keep increasing the voltage, the current is going to keep increasing, as shown here. Now, the specific way a Zener diode is different to a normal diode is in the reverse bias mode. So in the forward mode, it's going to be very similar to what you see here. But in the reverse bias mode, what did we observe is for a normal diode, when you reach breakdown here, where for when you keep increasing the voltage in the reverse direction, when you reach this breakdown voltage, for a normal diode, it means that you have a sudden inrush in current. The current is going to just increase drastically without any significant increase in voltage. And for a normal diode, this would mean the diode is broken, because when you have this inrush in current, this huge increase in current, basically this is going to create a large heat dissipation in diode, and this is just going to blow away your normal diode. But a Zener diode is designed now to actually operate in this region. So when you have a Zener diode, you would have a rating for this breakdown voltage, and when you actually exceed this breakdown voltage, the diode will not fail, as long as you don't exceed certain parameters which we'll look at. Okay, so Zener diode is typically operated in the reverse mode. If you have an application where you are using a diode in the forward mode, like for example, where we had the bridge circuit for a full wave rectification, so you would use a normal diode, because there is basically the forward mode that's into us. But if you have any application, as we see shortly, where in the reverse mode, you want to maintain a certain voltage in the reverse mode, then you would go with the diode. Okay, so this highlight very important discussion is the difference between a normal diode and a Zener diode. So just to recap, a normal diode would blow away when you operate it beyond the breakdown voltage because of a certain increase in current causing heat dissipation. But a Zener diode is able to operate in this region as long as we don't exceed the power the power specification that's specified on that specific diode. So we're going to look at that in a few minutes. So I'm shifting back now to the slide for the Zener diode, and we proceed. Okay, so as you've seen before, when we're discussing as a Zener diode, the normal diode rather, we have two mechanisms which explain the breakdown region. We have the avalanche breakdown and the Zener breakdown. So when we talk of Zener diodes, we are definitely, the name comes from the Zener breakdown mechanism, where we know that our diode is heavily doped. Be silicon or germanium diode is heavily doped, means being heavily doped, now your depletion region would be very small, and then you have a very large magnetic field that's created, because magnetic field is always V over D. So when your separation between your plates are very small, you get a very strong electric field. So this is what the mechanism causing this inrushing current. Okay, so as I've just mentioned, when we look at the characteristic curve for the Zener diode, for normal diode, we would have 4 Zener diodes, a specification of breakdown voltage, so it can from 2.4 to 200 volts. So for example, if you have a Zener diode specified with a breakdown voltage of 2.4 volts, it means this sudden increase in current that we had characteristically would be at 2.4 volts, and beyond 2.4 volts, if you exceed 2.4 volts, the Zener diode would not keep increasing the voltage across it, it would maintain it at 2.4 volts. So this is why a Zener diode can be used for regulation. As we've seen in previous lectures, when you have actually perform filtering on a full wave or half wave rectified signal, and then you have applied your capacitor to do the filtering, you still have few ripples. And then if you want to have a steady DC, so if you connect a Zener diode across that voltage, which is still having few ripples, you can have a steady DC based on this discussion we just had. So if you just read through that, we said the VI characteristic of a Zener diode is very similar to a normal diode, except that the breakdown voltage can be small and the Zener diode can operate in that region, whereas a normal diode will just blow off. So this is the symbol that you have for Zener diode. So exactly like a normal diode, except that now you have these two bars there showing a Z. Now, whenever you are using a Zener diode in the circuit, you would have to check a few things to check whether it is properly biased for the circuit and that you're not exceeding the power dissipation. So whenever you look at now a Zener diode, you would have important parameters that are different to normal diode. You would have a maximum power dissipation in the breakdown mode, and you also have the breakdown voltage. This is a very important parameter. So basically, these are the three things we need to check out. It should be reverse biased, because normally if you operate a Zener diode in the forward bias mode, it's just a normal diode. So you would not waste extra money to buy a Zener diode because it normally costs more. Okay, like operating it in the forward mode is nothing but a normal diode, therefore it doesn't justify high cost involved. So it should have a voltage across it greater than the Zener breakdown voltage, because if you look at the characteristic curve for normal diode and for Zener diode, if the reverse voltage you have across the diode is less than the breakdown voltage, it will not conduct. This is a region where you have the sort of very small leakage current and your graph is more or less horizontal, and this region, of course, the Zener diode will not conduct. So if you want to actually benefit from this important characteristic of the Zener diode to be in the breakdown region, you would have to apply a voltage which is greater than the ZZ, which goes with the breakdown voltage. Yep. And thirdly, the circuit current should not exceed IZ max. So you would have an IZ max which is specified. So basically, if you take IZ max, you multiply by VZ, you're going to get a PZ max in the reverse breakdown region. And if you exceed that, even then the Zener diode would fail, would blow off. So you have a maximum power that you can dissipate, and this maximum power is limited by the maximum current that can flow through it, because the product of VZ and IZ will give you power. Let's take some examples to check biasing of Zener diodes. So here in these four circuits there, we're trying to see if a diode is properly biased by applying these three principles we mentioned. Let's take the first circuit here. So we're applying here a DC of 15 volts, and then we have a resistor of 330 ohms, and this is your Zener diode connected in reverse mode. You can see the positive terminal battery is connected to the cathode and the negative terminal to anode. So this Zener diode is always in the reverse bias mode. So that's satisfying the first condition. Second condition, we have to check, do we actually have more than 12 volts connected here across it? If we check, yes, we have 15 volts. So this diode would take 12 volts across it, and the remaining 3 volts would actually appear across the resistor. So if you apply here, which I just annotate now. So if you have main current flowing, this main current will of course flow, this main current I will of course flow through your resistor and your diode. And whenever you have a voltage which is applied across the Zener diode, which is more than 12 volts, it would not allow the potential difference across it to exceed 12 volts. This is, we can see that actually on the characteristic curve for the diode or the normal diode. Whenever you exceed certain voltage, then you have a vertical region. The vertical region simply shows that now the voltage will not increase further. And like we said, a diode is able to operate in that region. So it means the voltage across here, when the Zener diode is in the reverse mode, and you have exceeded the breakdown voltage, which is the case now, you would not be able to go beyond 12 volts. It means this is going to be 12 volts. And if you apply Kirchhoff's voltage law, you find that you have 3 volts remaining here. And from these two now, you can calculate what current is going to flow here. So if you do 3 using Ohm's law, 3 divided by 330, so you get your current, and you just have to validate that this current actually doesn't exceed 4 milliampere. If it exceeds 4 milliampere, means this diode is not properly biased. The current should not exceed 4 milliampere. So you can check that. Let's go to the next one now. So in this case, you find that you're applying 6 volts across the diode with 10 volts. So there's no opportunity for this voltage to exceed the 10 volts. So basically, this diode would always be in the reverse bias mode, not in breakdown. So there's no opportunity for the diode to go into breakdown. So this circuit, I would say, is improperly biased, because you are not operating your diode in the breakdown region. It will be just reverse bias where you have the flat region. So actually this circuit would be, this would be cut off and no current will flow. So as you can see, it's not a very useful circuit. So there's no check to do for IZ max here and so on because no current actually flows. Okay. Let's look at the other two circuits now. So I'm just going to clear the explanations we had. Okay. Let's look at this one now. So you can clearly see here you have 15 volts connected, but just look at the polarity of your battery. So this is minus and this is plus. So basically you are connecting the anode of your, the positive terminal of your battery to the anode and the negative to the cathode. So this diode now is forward biased. So the current is going to flow like this. Okay. In the forward bias mode, definitely you can, as we've seen, you can just short circuit this diode if you assume idle diode. So it's just going to be normal diode operation in forward bias mode. You can just assume this is like a short circuit, and in that mode there it means your diode is not reverse biased. So this diode is not reverse biased, so it is like a normal diode. So I would say here again, this diode is not properly biased. If you wanted to have an application like this, you would simply use a normal diode here. And very careful, the IZ max we are mentioning here is when the diode operates in the reverse breakdown region. So it's not that current which is flowing now, which you take 15 divided by 330, and then you get the current. This is not this current. It's when it's actually in the reverse mode, or when you have exceeded the breakdown voltage in the reverse breakdown region, then you find the current. Okay. So this circuit as well is not properly biased because your diode is not in reverse bias. Let's check this one now. First thing, when we check the polarity of your batteries, this is positive here and try to be connected to the cathode. So there's opportunity for this diode to be in reverse bias mode. So in terms of connection of battery terminals, it seems okay. Now, next thing we have to check is actually the voltage across this diode exceeding 12 volts. If it is not exceeding 12 volts, it means it is not in the breakdown region and it's a useless use. It's not a proper use of this diode. So how we do that, we can see now this diode is connected in parallel to this resistor. So we can apply the voltage divided equation, which we know. So it's, if you do 1800 divided by the sum, so 3000 times 24. Yep. So how much do we get? This would be the voltage that we get across this diode. So multiply by 24. So we're getting 14.4. Okay. So we're getting 14.4. Okay, so we get 14.4 volts. That's what you would get if there was no Zener diode. But now when you're trying to apply 14.4 volts across this Zener diode, it would limit, because you're exceeding the breakdown voltage, it's going to limit the voltage to 12 volts only. This is very important. So in the absence of a Zener diode here, you would get 14.4 volts across the 1800 ohm resistor, and the remaining one would appear across your 1200 ohm resistor. But since now these two are connected in parallel, and when you try to exceed the voltage across this diode, you try to exceed the breakdown voltage, it will not allow this, because this is why you have this region here, and it just falls drastically in the reverse mode. So if that value here is your 12 volts, which you're exceeding, if you exceed beyond that, as you can see on the curve, it does not increase, it just remains at more or less the 12 volts. Means when we connect now this diode in the circuit, it's going to maintain the voltage across itself at 12 volts and across the resistor as well, because they are in parallel. Now, remaining one, if it's 12 volts, then 12 volts has to appear here. It's 12 volts appearing here. So if you apply now Ohm's law, you can know what current is flowing here. If you take 12 divided by, so if you take 12 divided by 1200, so you get 10 milliampere. So we've said that 10 milliampere is the main current that's flowing in the circuit. Now, when the current, of course, comes here, it has to split into two paths here, applying Kirchhoff's current law. Now, how we determine what current is flowing? We know we have 12 volts across, because 12 volts is across both the diode and the resistor. So if we take 12 divided by 1800, so we find that we have a current of 6.67 milliampere. So this current here, if we take 12 divided by 1800, so we get 6.67 milliampere is flowing here. Okay, so you have a main current of 10 milliampere. Now, if 6.67 milliampere is flowing through here, so 3.33 milliampere has to be flowing across the Zener diode. And if you cross-check now, this value against the maximum allowed, so it is below that. It means the Zener diode is in a safe operating region. So this circuit is properly biased in terms of polarity, first thing, in terms of current that can flow through it, and in terms of potential bias. So this circuit is properly biased. You can see it's properly biased. It's going to operate. We're going to make effective use of the properties of this diode. Okay, so let's move ahead. Where do we use Zener diodes? Like I've just mentioned, you can use it for voltage regulation. If you want to provide a fixed reference voltage, you can use it also in clipper circuits. We're going to look at that in a few minutes. You can use it in meter protection because the current, the voltage across a Zener diode cannot exceed a certain region, even if your input voltage is increasing. So that can be used to protect devices. And of course, you can use it for reshaping waveforms. Let's consider a few examples now to illustrate this. If you have a circuit like this, which is very similar to what we've just seen earlier, but now instead of connecting a DC, you're connecting an AC here. If you're connecting an AC here, and the AC has a peak value of 50 and then minus 50 on the other side, and we want to sketch the out expected flow signal for an ideal diode. Okay. Now, to be able to sketch the this curve, you would need to know the value of R and RL, of course, because that determines whether what voltage are you actually getting across the diode. Yeah, so we can put values for this R and RL and try to see how the circuit behaves. So this circuit is very similar to this one, as you can see. So you have two resistors, and here, and one is in parallel to the diode. Very similar circuit here, and so I would ask you to give this a try and put different values for R and RL here. So we have some examples which I'm going to cover here. Yeah, very similar examples. So in this one, you can try to put different values. For example, you can put 1K here and 1K here. And then if you do that, if you put 1K and 1K here, so both R and RL are the same. So if you forget the Zener for time being, what voltage actually you get across RL would be half of VG. Yeah, so it means as your input voltage is changing, of course, when your sinusoidal waveform is in the negative mode here, so you are simply having a current that's going to flow here, and it's going to have a short circuit of this one. So it means you're short circuiting RL. You just have this path, which is going to be relevant. So basically, in the reverse mode, you would simply measure 0 here. So I hope it's clear. When you, let me just repeat that. So if you're in the negative half cycle you have here, it means you are now sending current in this direction, and so this becomes forward in the forward mode. In the forward mode, this is like going to be a short circuit. So basically, no current is going to flow through RL, and your V out will be 0. Okay. Now the interesting part is in the half positive cycle here. So in the half positive cycle, you have two possibilities for your Zener diode. One is when it's in the breakdown region. Yeah, so it has exceeded your breakdown voltage, but the other possibility is it is in the reverse mode, but not yet in the breakdown region. It's just in the reverse mode where you have no current flowing. So it's like an open circuit. Yep. So if you take a simple case where both of these are equal, so R and RL are equal, so you're going to get half of your applied voltage across RL. So if, for example, it is 50 here, so you get 25, and in that case, 25 would exceed the 20 volts. But the Zener diode will not allow it to go beyond that level. It's going to stop it at 20. Yeah. So if you just do an analysis like this, you will be able to do a sketch. Let me just try to annotate now and take the specific case we are looking at. So if, let's say, this is 1K and this is 1K, for example. Okay. So in this situation here, we can see clearly that your voltage across RL would tend to be half of the applied voltage. Okay, so the question now is, when is this applied voltage in the positive half cycle going to exceed 20 volts? Okay, so if it is, for example, because we say it is half, if VG now is 40, if you put a value of 40 volts, so if when your applied voltage is 40, since it's going to be shared equally between these two, if they have equal resistances, so you have 20 volts that would start appearing across EV out, and that's exactly what the breakdown voltage is. So this is a very important threshold. This is where your diode will start going into breakdown and prevent the voltage from increasing further. So what can we infer from there? If we take another example, if we assume now, if we take an example, let's say your applied voltage is at 30. So let's say if we had 30 volts applied here. If you have 30 volts applied here, like we apply the voltage divider rule, we find that we have 15 volts across this one. 15 volts is less than the breakdown. So if you consider the characteristic curve, if I just draw that, sketch that here. So in the reverse mode, we know this is how it behaves. So for this diode here, we're saying that this is 20 volts here. So if we're applying 15 volts across it, it's going to be in reverse mode, but not in breakdown. So normally in this mode here, we simply assume that the diode is not there. It's just an open circuit, like we've done for a normal diode. So it's just like a normal voltage divider. And what are you going to measure here? You're going to measure half of this. So you're going to measure 15 volts. Yep. So you can just sketch below it. Yeah. So this is your V out. So what are we observing here is the 20 volts that you have is an important threshold, and this is going to be a determinate line. Determinate threshold. As long as we are in the positive half cycle, but less than 40 volts, we're going to get half of it. So at 40, we're going to get 20. So this is the threshold here. So it's going to increase to 20 output. And on the same way on this side, we'll get 20. Now, important when you try to go in the negative half cycle, as we'll explain, it's going to be in the forward mode now, and the V out will be simply 0. So this is going to be 0 when it is in the negative half cycle. Okay, so this corresponds to the negative half cycle. Now, what we need to find out last is when it actually exceeds the breakdown voltage, which we get for these particular values of RL. If we exceed 40 volts, then the voltage across RL will exceed 20 volts, so to exceed the breakdown. And this is where you would get now 20 volts fixed. So when you exceed that, it's going to be fixed at 20 volts. This is the operation of Zener diode. When it exceeds the breakdown voltage, it's going to maintain at 20 volts. So this is going to be fixed now at 20 volts. And the remainder, of course, would appear across your resistor R here. Okay. So if you apply a similar analysis to this, circuit here, and here you can see we are already giving, it's not an AC, the input is not an AC, it's a DC. So let's just take a few situations there and see how it works out. So our V-in is being changed here. So it is 36 volts and then 27 and then 22. So we want to see what V-out do we get. So V-out is basically the voltage across your resistor R, and also because these two are in parallel, the voltage we get across those in the diode. And you have as a max also to check whether you're exceeding the maximum current or not. So in this situation here, you can see your RL is 1.5K. So if you want to calculate for the maximum voltage, you have 36 volts. If you want to calculate what RL would you get, so you would take 1.5 divide by 4.7 plus 1.5, so simple voltage divider equation, multiply this by 36, you're getting 8.8 volts. Now, if you try to do that, if you try to take 1.5 divide by 6.2, the sum, and then multiply this by 36, getting 8.7 volts. So if you have the maximum voltage you can get across the resistor is 8.7 volts, never going to exceed your breakdown voltage. So it means in this case, your breakdown voltage will never be exceeded, and this circuit will be simple voltage divider. So it's not very useful in this case. Now, next scenario I want to consider is what if we change this value here? So we change this value of resistance here to a value of, let's say, 7K. Yep, so let's increase that to 7K now. So if we start doing the same analysis now, if you take 7, divide by, same like we've done, 4.7 plus 7, and then you multiply by 36, now you get a voltage of 21.5 volts. So you can see if you increase now this RL to 7K, you're getting a value which is above the 16 volts. So it's in breakdown region now, and that Zener diode now would not allow this voltage to go at 21.5 volts. It's going to maintain at 16 volts. Okay, so for this situation here, if you apply 36 volts, we find that the V out would simply be 16 volts. It would not allow it to go beyond that. And in this situation, if you have 16 volts here, the remaining would have to appear across your resistor of R. So like we've done in the previous case, if you have now 36 volts being applied and you have 16 volts across your diode and your resistor RL, the remaining is 20 volts, and then you divide that by 4,700, you get the current of 4 milliampere. 4 milliampere, getting 4.2 milliampere. So if 4.2 milliampere is flowing here, there's no reason why this current would exceed 10 milliampere. If it was above 10 milliampere, then you would do a similar calculation like we did. So you calculate these two paths current, and then if it check if the current flowing through this diode is 10 milliampere. So in that case, we're getting around 4 milliamperes and no issue. Now, what if we maintain 7K here, and what if your VIN now drops to 27 volts? So similar calculation now, you would take the 7 divided by 11.7, the summation of the two resistances, the voltage divider, multiply now by 27, we're getting a voltage of 16.2 volts. So 16.2 volts, again, is above your 16 volts. So even in this range here, the output V out would be 16 volts because you're exceeding the breakdown. It's going to be 16 volts, and the 0.2 volts, if you want, is going to appear across the resistor R here. So very small current is going to flow. But even here, for 27 volts with an RL of 7K, you're going to get the diode in a breakdown region, and so it's going to maintain at 16 volts, not at 16 volts. Now, if you put now the in at 22 of volts, the same calculation, assuming it is 7K, so you take 7 divided by 11.7, multiply by 22. Now we get a voltage of 13.2 volts here. So if you get 13.2 volts here, it means it's not exceeding your breakdown voltage. It means this diode is simply an open circuit. You just get a simple voltage divider. In this case, your V out would be as calculated because it's not exceeding your 16 volts. It's going to be 13.2 volts. So as you can see, the value of the RL here is very important. Is very determining here in this case. It's determining whether your diode is going into breakdown region or not. Okay, so do consider these different scenarios on your own and see whether it makes sense to you. Okay, so we've covered this already. Now let's see how can we use this Zener diode for diode protection. Yeah, so we've mentioned that we can use diode for meter protection. So let's consider these cases here. So sketch V out for the following circuits with VG being a sinusoidal waveform of peak 30 volts and frequency 50 Hertz. Yeah. So if you were to apply now a sinusoidal voltage to this one, for example, so if this one is pretty simple, if you are in your positive half cycle, you can clearly see here, you will be in reverse mode, but whatever is in diode is in reverse mode. It's very important to know whether it is in breakdown region or in normal, just a reverse mode. So whenever you exceed 10 volts now, this is going to maintain 10 volts across it. If you don't exceed 10 volts, then this diode will simply be an open circuit and no current is going to flow. When your waveform now is exceeding 10 volts in the positive half cycle, then you would have a situation where 10 volts is going to be maintained here and the remainder would be flowing across. So the remaining potential difference would be across R here. In the negative half cycle where you're flowing, you're trying to flow current in this direction, then this would simply be a short circuit. Now, I want you to consider this one now, where you have two diodes connected back to back like this. So in both cases, when you're trying to send current in this direction, this would be a simple short circuit. Then this is going to be active. And when you do the reverse now in the negative half cycle, then this one will be a short circuit and this one will be active. Do you consider how V out varies for this input waveform? In this case here, very similar to what we have here, simply you have different breakdown voltages for your two diodes. So in forward mode, when you are trying to send current in this direction, so the 15 volts is going to be the 15 volt breakdown voltage in diode is going to be forward bias mode, so you can just put a short circuit here. But this one will be active beyond 18 volts. When the voltage applied across it is beyond 18 volts, it's going to maintain 18 volts across it. And the when you have the negative half cycle of your sinusoidal input waveform, when you try to send current in this direction, then the 18 volts one is actually forward mode. And whenever the voltage exceeds 15 volts, then you have 15 volts across the out. So I would encourage you to sketch all these, and we're going to consider that in the tutorial class. Okay, so this is where I'm going to stop here for the video on Zener diode. So do consider this on your own, and do get back to me if you have any problem. Thank you.